Thank you for the introduction, and thank you all for sticking around for the last section. I'm Will Kindel. I'm a team leader in one of our technology teams at IQM, and I'm here to present upon the results of and present a novel QPU we've developed that has a computational resonator in addition to standard transmon qubits. And I think this is a very apt environment in that we're looking at creating these new types of interactions and probing some of the higher levels of the resonator. So this is what I'll be talking about, conceptually shown. So we have a essential element, which is a computational. We have a question? Can you just talk a little louder? It's a little bit loud. Okay. All right. Thank you for the feedback. So conceptually, we have this QPU. Is this one better? Maybe this one's better. I'll use both. We'll figure it out. So conceptually shown, we have a QPU with a central element, which is a computational resonator. And around it, in this particular device, we have 6 satellite qubits. Additionally, each qubit has standard readout resonators and all that. Those are not shown in this simplified picture, just to emphasize that the computational resonator is completely distinct and holds quantum information. And in this computational resonator, there's 2 ways we can think about it. One is we can use it to encode a qubit, which is consistent with a standard gate-based model of quantum computing. Another way is we can explicitly access the higher levels and move beyond qubit encoding, which is at least breaking the gate-based model for qubits, which is, in terms of the hierarchy of models, one way that you can break it. And because of this new element, we've developed a new gate set. One is a controlled phase between a qubit and a resonator, which is in a qubit encoding a equivalent to a standard qubit-qubit controlled phase. And then we have an exchange operation that, depending on how you use it, we give it a different name. If it is just shuttling an excitation into the resonator to do the encoding, we call it the move. And then if we are interacting to access the higher levels, we refer to it as a Jaynes-Cummings gate because it implements a Jaynes-Cummings type interaction. And then in the spirit of this talk, something that we are working on is adding explicit time control is another way to break the gate-based model. And here I am telling you about this, but I would like to know what kind of features you would like to have so that we can develop and provide them and provide QPUs as a tool for you. So IQM, just to give a little overview, we are a European company based in Helsinki with a large technical presence in Munich. We have a few other smaller offices, and we sell fully functional quantum computers that accept high-level programming. We have shipped 6 systems, including 2 20-qubit machines in Finland and Germany. And additionally, we have a cloud platform available. Just to give an overview of our baseline technologies, we have initially started developing square lattice QPUs using transmon qubits and tunable couplers. We have offerings and devices spanning 5 qubits, 20 qubits that we have shipped. A 54-qubit device we are currently have acceptance testing, and soon we're on the process of developing 150-qubit QPUs. Now, to go into some more details, I want to share the performance of our devices at different scales. And this is just a snapshot of where we are today. At the scale of test devices, so these are simplified devices with just 2 qubits and a tunable coupler between them, we have been able to achieve lifetimes and coherence times at the order of a millisecond. And this has allowed us to achieve our 2-qubit gate fidelities at the 99.9. Then as we increase the scale to 20 qubits, we have 2-qubit gate fidelities, median 99.3. And then Currently, in our testing of the 54-qubit device, we have, in a 48-qubit subpatch, median 99% fidelity 2-qubit gates. And if you are interested in seeing the performance yourself, you can go onto resonance.meetiqm.com, create an account, and we offer a free trial for you to try out either our resonator star QPU or a 20-qubit QPU, and you can try the performance yourself. And these are the numbers of the performance of the 20-qubit square lattice when I made this slide on October 3rd. But today, we are talking about breaking or moving beyond the gate-based model. So I want to talk about not our square lattice QPU, but this QPU with the central resonator. And so I introduced this to begin with, that we have the ability to, that we have this bosonic element, that we can do different encodings. And I'll just jump into talking about some high-level applications that we've been thinking about without going into the specific details. In partnership with HQS, which is in Germany, we've been investigating potential applications where this is some of their ideas at looking at highly reactive molecules. If you consider benzene, it has, if you look at all the levels, it is quite daunting. But there's a lot we can effectively ignore. All the occupied ones, we mostly ignore. All the higher level ones, we mostly ignore. And then you can zoom into where all the reactions might happen. And our tools that we might attack this problem with on a QPU would be having ones with resonators in qubits, and at the scale of potentially tens of resonators and tens of qubits, we might be able to do interesting calculations that could not be done classically. But this is a bit high level. To get a little more specific, in a more toy model, you can consider the Hubble-Holstein model. Here is a particular reference where they took this model of chemistry, they mapped it onto qubits, and in this reference, they dropped some terms. These particular terms, we believe, could be represented using qubits and resonators in a Jaynes-Cummings-like interaction. Now, the other aspect of the QPU is the connectivity. It has this one-to-all, which could be mapped to certain types of problems. And additionally, this gives us an element which we can use to create longer distance connections, which this can be useful for different types of error correction codes. For example, if you consider, it is now broadly known in the field and QLDPC codes that if you move beyond 4 parity checks and add longer distance connections, you can get codes that work much better in terms of their performance, given a certain number of physical qubits and how many logical qubits you can encode. They can be much more efficient if you add these additional capabilities. All right, so now I want to talk a little bit more about how it is we do these interactions. On the left, this is that cartoonish picture, and then what I'm showing is a more representative circuit model. And you can see we have our qubit, it has a tunable coupler, and then this is connected to a resonator. We apply our gates by first flux tuning the qubit. If we want to do something like a Jaynes-Cummings gate, we would tune it in resonance. And then we add a flux pulse on our tunable coupler. When the coupler is idling, we have it so it's nulling the ZZ coupling between these two elements. We turn it on, it interacts, and then we turn it off. Yes. The question is asking about the connectivity. There's one central element. This central element in this QPU is connected to directly connected to 6 tunable couplers. And then each of those tunable couplers is connected to a respective transpond qubit. Okay, so now now I'd like to talk about how we tune up the operation where we exchange information between a qubit and a resonator. This interacts with the James-Cummings-like Hamiltonian. If we apply a sequence where we excite the qubit, tune the two elements in resonance, and then measure, we can do a measurement of the population exchange where we vary the interaction time and the qubit flux amplitude or the qubit frequency. This allows us to calibrate the interaction that performs this exchange. Additionally, if we want to stick with just qubit encoding, we cannot run this interaction when both elements are in the excited state, because then we can populate the higher levels of the resonator. All right, so now that I've talked about this new type of operation, which we call the move, we need to benchmark it. And there's a couple factors we need to keep in mind when we develop our benchmarking routine. We do not have native readout on the central resonator. Additionally, we have no displacements or anything like a single qubit rotation available on resonators. So instead, we benchmark the move in a sandwich, where when the resonator is empty, the move is its inverse, so doing two back-to-back is an identity gate. And then secondly, when we benchmark the qubit resonator CZ, we likewise sandwich it between two moves, where when the resonator is in the ground state, this 3-gate circuit shown is equivalent to a CZ between the two qubits. So we can do interweave randomized benchmarking with the double move. On our best device, we get these fidelities shown here, 99.6 for the double move. And here is just here's a table just showing all of our coherence data on this device at this particular moment in time. But I'm more interested in showing what you can do with it. And one simple example in the gate-based model is we can construct a GHZ state. This is just to show you how everything works. You can do this by applying a Hadamard on a qubit, then you apply a move, then you do a series of controlled knots, and then you move back to the qubit, and then when you measure, you get all the populations, which is shown here. Now, to get the fidelity, we have half the information we need. In addition to the populations, we need to understand the coherence. This can be seen if you think about the density matrix, where for the GHZ state, the density matrix has 4 components. 2 come from the population, 2 come from the coherence. To get the coherence, we will construct a GHZ state, we apply a single qubit rotation, and then we deconstruct the GHZ state, and that rotation gets mapped upon our initial qubit. And if we look at the interference fringes and their visibility, we can extract the fidelity. With these 2 pieces of information, we can get the GHZ state fidelity, which I've shown here. This was data from February. Since then, we've adopted the GHZ fidelity as a standard diagnostic measurement, where in the queue, every hour, we measure the GHZ state fidelity. And what is shown here is just the measurement from August, where you can see we have fidelities hovering, for the most part, in the high 60s to 75%, except for a couple events. Those 2 events both corresponded to 2 of our qubits had a drop in coherence that then went away. Okay, so I have introduced this QPU. I've talked about how you can use it with the gate-based model. Now I want to get into how we access this higher level of the resonator. And the way we access is with the James-Cummings interaction. The move operation, which we use to shuttle, is actually a James-Cummings interaction, and if you consider the full matrix, you get all of these different terms that will excite the resonator. We can construct a simple experiment to show how this works, just looking at the populations. So we take a qubit, we excite it, we apply a move operation, then we excite the qubit again. At this point, both the qubit and the central resonator are excited, and then we apply this move operation, which is described by this gate here. And this gives us a predicted probability distribution, which this is a sanity check to show that we are indeed accessing the higher level in a way that we think. But this is just showing the populations, and nothing about the coherences really affected this operation. So if we want to do more sophisticated things, we need to consider some of the phase dynamics of what a real Jaynes-Cummings gate would happen. So we have, if we consider the qubit resonator system, we have some ideal phases. An example of an ideal phase would just be the number-dependent phase that any state in the resonator would acquire. Additionally, we have phases that are due to the fact that when we apply the gate, we tune the qubit from its idling configuration into resonance with the resonator, with the computational resonator. And usually, we think about our quantum information in the rotating frame to remove all time dependence. That is, we have a computational frame that every element is rotating at its idling configuration. Now we need to think about a different frame, which is the frame of the interaction. In this frame, everything is rotating at the resonator's frequency. The effect of this change of frame results in acquiring phase with terms that come at the difference frequency and grow with time. So we have time-dependent phase shifts due to this change of reference frame. And then the last type of phase shift we need to be aware of are phases that are just due to the dynamics and level shifts of our gate. So to show how this works, we perform this experiment, which has two parts. In the first part, we just simply load an excitation in the resonator. Then in the second part, we perform what would be a Ramsey sequence if the resonator is empty. That is, we partially excite a qubit, try to move that into the resonator, wait a certain amount of time, move it back, and try to undo that rotation. But in this type of sequence, we have an interference from 3 different terms that correspond to different occupancies of the resonator. Here is a little tree showing all of the different terms that happen once we start the Ramsey sequence. But the bottom line is that at the end of this, we are left with we expect to see this probability that has 2 time-dependent terms. One is coming from the resonator in the 1 state, the other is coming from the resonator in the 2 state, and we expect to see a beating pattern. When we perform this measurement, we do in fact see a beating pattern with the right frequencies, but they have phase shifts that are non-ideal. And this is a plot of showing this experimental result with the ideal prediction and no fit parameters whatsoever. Now, if we add some of these non-ideal phase shifts and recalculate what we predict, we get 2 extra phases that get added onto these beating terms, which we can do a 2-term phase fit, and we see really good agreement between the data and what this gives. So going one step further, we now want to see about correcting these phase terms. So what we do is we add real rotations on the qubit after the two moves. We use values determined from the fit in the previous experiment to set the rotations. And this should give us what our original expected value is. And now I'm plotting, once again, the experiment with the ideal theory and no fit whatsoever. And this is showing how one can master and understand the phase dynamics of the Jaynes-Cummings gate. So today I've talked about using qubit resonator QPUs in two different modes. One mode where we're treating the resonator like a qubit and is very much in the vein of a gate-based model. The second way is explicitly controlling these higher levels and looking at time dynamics. So, to conclude, what we are trying to do is we are trying to build tools for quantum scientists. I've talked about and presented two different types, the square lattice QPU and our qubit resonator star QPUs, and I'm really interested in learning what kind of features you would desire, especially if you're interested in some of these analog simulations, what kind of features and controls you desire. I've talked about qubit resonator QPUs, shown generating GHZ states and populating the higher levels with the Jaynes-Cummings gate. You can try these QPUs out yourself. Right now, the use is limited to the gate-based model, but starting early next year, we are adding full timing and pulse level control, which would allow users to do some of the experiment that I showed with the Jaynes-Cummings gate. Going forward, we are interested in scaling, and we're scaling two different ways. One way is coming with larger stars with more qubits attached, and the second way is we are thinking about how we are connecting stars to make a larger QPU capable of implementing different types of quantum error correcting codes. And with that, I'd like to thank you all for your attention and for sticking through to the final section.
So questions?
Yeah, very nice talk. So this looks very similar to the shared modes, looks very similar in trapped ion where you have some motional modes that's shared by all the ions. So can you comment on, some of the, and also Jaynes-Cummings is also widely used in trapped ion, actually not the conditional displacement. Can you comment on the advantages, disadvantages of this architecture as compared to trapped ion, or what it can do more or less, or what's its benefit on that?
Okay, great question. My cheeky answer will be, we are trying to get the benefits of superconducting qubits in trapped ions. But there are some important differences. One is in terms of the energy scale. Like in a trapped ion system, all the elements are connected through a harmonic mode. But in the trapped ions, that is megahertz frequency, which means that the types of gates, the types of 2 qubits gates that they do cannot really be done because of a completely different frequency regime. Which is a limitation we have compared to trapped ions. But the counterpoint is that these resonators are very high Q and at gigahertz frequency. So it can be a tool for processing and holding quantum information.
I see. Yeah, I have an idea that you might be able to use the resonator to do a resonator control the different qubit operations on all the qubits. So it's like a single instruction, multiple parallel operation. But just some idea, I think it's possible with your architecture.
Yes, that would be very interesting to implement.
Yeah, thanks. Really cool talk. I was wondering, so in many of these sort of cavity qubit experiments, you're kind of in the dispersive regime as well. Can you access that as well, where the qubit and the oscillator are sort of highly detuned from each other?
Yes. So the short answer is yes. Like you have the ability to tune the frequency of the qubit and control the interaction strength. One caveat is you can only tune the frequency of the qubit down. And for most of our devices, we are targeting just, let's see, so the qubits have an anharmonicity of about 100 megahertz, and we are targeting a maximum frequency of around 150 megahertz above the resonator. So if you wanted to be far detuned, you would need to tune the qubit down in frequency quite a bit, which would move it away from its flux and sensitive point and decrease its coherence.
I see. Okay. And sorry, one more question. You were mentioning they were high Q. So what exactly is the lifetime of the cavity compared to the qubit?
I have.
And do you just have T1 on the cavities or also T2?
I have a slide somewhere. Okay, I'm going to exit. All right, so this is T1 measurement and T2 measurement of one of our resonators, and we have a lifetime of 15 microseconds and coherence of 30.
I see. So no T2 basically, right? It's just, yeah, cool.
Yes, thanks. I guess I'm just curious. You mentioned like it cannot do displacement. Like I'm kind of curious, maybe from a series, like is that like a design choice? Like what happens if you add some driveline to the resonator? And alternatively, is it possible to use the qubit as like a mediated, like kind of to act as drive on the resonator? Maybe
Yes,
like
great
related
question.
to the trapped ion.
We have heard from a handful of people who would be interested in displacement operations. Currently, we did not design it with a direct displacement drive on the central resonator. We've hypothesized that using one of the qubit drives and simply driving at the resonator frequency would work well. We have not investigated whether or not there would be anything terrible happening to that specific qubit.
Right. So that's not like a fundamental limit in terms
That is
of,
not a fundamental limit at all.
Are there more questions?
So on your IQM website, you say that the 5-qubit device is an affordable access to quantum computing. I wonder how affordable it is.
That is a great question. I am not a salesperson. I cannot give you exact figures, but I will say that our strategy is not to make money off those devices, and they are sold just slightly over the cost of all the equipment, including the electronics and dilution fridge.
Oh, you mean the actual unit?
Yes.
That's
Like-
1 million. 1 million euros.
That's, yeah, roughly speaking.
Yeah, I mean, I heard that because I spent 3 hours in the company. I heard that number. But this is also what I heard that they say like if you just buy all the components, the prices are higher than 1 million. That's also what I was told.
It is priced just over, which I think is,
Yeah, it's just over.
yeah.
Very affordable. But I think the message is that if you have $1 million, you can have the entire thing put in your lab. It's gonna work. Yeah, and you can maybe swap you can just fabricate your own chip and put it in. That still works. Yeah, that's what I was told. Are there more questions? No. Let's just thank Will again.
Thank you all.
So that just concludes our all talk. Thank you. And actually thanks for everyone just stick around until the last moment of all the talks. But we have a poster session. There are like foods, but in another location in the Quicks. So if you haven't got a chance to visit Quicks, this is the time. But of course, I think a lot of people are local here. So maybe we can just move to Quicks. There You can put your poster on, and we have freshmen there. But also you can grab for here as well. We paid for those things as well. So and thanks to everyone for coming. I think that's what we have for this workshop. Yeah.